What if the universe you're standing in right now is actually the inside of a black hole? Stay with me, because the math behind that idea is uncomfortably convincing. Take the total mass of everything we can observe, run it through the same equation that defines a black hole's edge, and the number you get lines up almost perfectly with the size of the cosmos itself. We'll get to exactly why at the very end. For now, let's build up to it. 7 levels of black holes, from the smallest thing physics allows to something so big, it might not even be a thing anymore. Level 1. The ghosts of the Big Bang. Forget the funnel-shaped monsters from the movies. Some of the earliest black holes theorized to exist might have been smaller than a single atom, and yet packed with the mass of a mountain, maybe even a small asteroid. Tens of billions of tons, folded into a point too small for any microscope ever built to resolve. If one of these things shot through Earth at full speed, there'd be no explosion, no crater. It would slip through the planet like a needle through fog, leaving nothing behind but a whisper of a seismic tremor and a gravitational nudge too faint to notice unless you were already looking for it. So where do objects like this come from? Not dead stars? Stars didn't exist yet. In the first sliver of a second after the Big Bang, the universe was a boiling, ultra-dense fog of energy, expanding faster than anything before or since. That expansion wasn't perfectly smooth, and wherever the density spiked past a certain threshold, gravity could win on the spot, crushing a pocket of that infant universe into a black hole before atoms had even formed. But nothing gets a free pass from physics forever. Stephen Hawking's great insight was that black holes slowly leak energy back into space and evaporate, and the smaller they are, the faster they go. The tiniest primordial black holes would have blinked out almost immediately. But ones born with the mass of an asteroid could still be evaporating today, billions of years later, and the finish line isn't quiet. It's a final, blinding burst of gamma rays as the last scrap of mass converts straight into radiation. For over 15 years, the Fermi Gamma Ray Space Telescope has been watching the sky for exactly that kind of flash. So far, nothing conclusive. That doesn't rule primordial black holes out. It just means they're rarer nearby, or hiding at masses and evaporation rates we can't detect yet. Level 2. Stars that ran out of time. Now we leave theory behind for black holes we can actually prove exist. Every star spends its life in a tug-of-war, fusion in the core pushing outward, gravity pulling in. That balance holds as long as the fuel lasts. Eventually, it doesn't. Once a star's core turns to iron, fusion can't squeeze any more energy out of it, the outward push vanishes, and gravity wins outright. If what's left behind is more than 2 or 3 times the mass of our sun, nothing can stop the collapse. The outer layers detonate as a supernova, while the core keeps falling, forever, into a point of no return. A black hole is born. These typically weigh a few to a few dozen solar masses, and our galaxy alone may hide tens of millions of them, almost all invisible unless they're feeding on a companion star or colliding with another black hole. That collision scenario actually happened, and we caught it. In 2015, LIGO detected 2 black holes merging far outside our galaxy, converting roughly 3 solar masses worth of matter directly into ripples in space-time that crossed the universe and reached us here on Earth. What was left behind, dozens of suns worth of mass, crushed into a region a few hundred kilometers wide. Level 3. The black holes. That shouldn't exist for decades. There was an awkward gap in the black hole census. We had stellar mass black holes. We had galaxy-sized giants, but nothing solid in between. Objects in the hundreds to thousands of suns range were suspiciously absent. Part of the reason, a single star can't easily make one. Around 100 solar masses, a dying star can run into the pair instability effect. The core gets so hot that photons start turning into particle pairs. The pressure collapses, and the resulting explosion can obliterate the star completely, leaving no black hole behind at all. It took until May 2019 for gravitational wave detectors to finally catch a black hole in that forbidden zone. The event, GW190521, recorded two black holes, about 85 and 66 solar masses, merging into one. Simple addition says the result should weigh around 150 suns. Instead, the final object came in at about 142, with the missing mass radiated away as gravitational waves. The leading explanation for how objects like this form, repeated mergers, black holes in crowded stellar clusters colliding and swallowing each other again and again, climbing into the forbidden range, one collision at a time. Level 4. The anchor at the center of the galaxy. Nearly every large galaxy has one of these buried at its heart, with masses starting in the millions of suns and climbing into the billions. Ours is called Sagittarius A star, weighing in at around 4 million solar masses. Swap it in for our Sun, and its event horizon would still comfortably fit inside Mercury's orbit, small by black hole standards, but with enough gravity to eventually unravel the entire architecture of the solar system. We can't see it directly. Dust clouds block the view, but we can see its fingerprints. Stars near the galactic center whip around an invisible point at speeds topping 24 million kilometers per hour. Orbits that only make sense if an enormous compact mass is anchoring them. In 2019, the Event Horizon Telescope linked radio dishes across the planet into one Earth-sized instrument and captured something no one had ever seen, not the black hole itself, but its shadow, silhouetted against a ring of glowing plasma at the center of the galaxy M87. Since then, astronomers have noticed something stranger. A galaxy's central black hole mass tends to track the mass of the galaxy around it, as if the two grew up together. Nobody's entirely sure yet which one is steering the relationship. Level 5. The quasar that shouldn't have grown this fast. One of the most massive black holes on record powers the quasar TON 618. Mass estimates vary depending on the method used. Some studies put it around 40 billion solar masses, others closer to 66 billion. But either number puts it in a class most black holes never reach. Its light has been traveling toward us for over 10 billion years, meaning we're watching it as it looked when the universe itself was still young. Around it spins an accretion disk so violently heated that the whole system outshines the sun by hundreds of trillions of times, bright enough to nearly erase the host galaxy from view. The real puzzle isn't just the size, it's the timeline. There's a physical speed limit on how fast a black hole can feed, the Eddington limit. Feed it too fast, and radiation pressure shoves incoming matter away before it falls in. Growing at that rate from a normal stellar seed shouldn't have given TON 618 enough time to reach this mass. The leading explanations, either it started from a giant seed, a whole cloud of gas collapsing directly, skipping the star phase, or it broke the speed limit for a while. Level 6. The black holes. Nobody has ever found. Astrophysicists already have a name ready for something we haven't detected yet. Stupendously large black holes, starting above 100 billion solar masses. Purely hypothetical, not one confirmed example exists. So why bother naming them? Because something that massive wouldn't just tug on a galaxy, it could steer entire galaxy clusters. Some theorists have floated the idea that objects like this could account for a slice of the universe's dark matter. It's a genuinely speculative idea with tight constraints. Anything too big or too common would leave fingerprints in the cosmic microwave background that we simply don't see. Level 7. The one we might be living inside. This last one requires you to throw out your mental picture of what a black hole is. We tend to imagine infinite density, a mountain's worth of mass folded into a space smaller than a proton. But the math tells a different story as black holes get bigger. The more massive the black hole, the lower its average density. Scale one up to supermassive size, and its density starts to resemble ordinary water. Scale it up to the size of a solar system, and it would be no denser than the air around you right now. Run the numbers for an object with the same average density, and the same size as our entire observable universe, and you land on something remarkable. The result matches the actual scale of our cosmos, within the same order of magnitude. This is where solid astrophysics ends and speculation begins. A handful of theoretical models explore the idea that our universe could be the interior of a black hole embedded in some larger, unseen space, and the equations describing gravitational collapse and cosmic expansion really do share an unsettling resemblance. To be clear, this is not an established finding. It's a mathematical coincidence, striking enough that physicists keep circling back to it, which leaves us with a strange thought to close on. We started this list with objects too small to see. We're ending it with the possibility that the largest structure in existence isn't an object floating somewhere out in space. It might be the boundary we're all living inside. What do you think? Coincidence or something more? Drop your take in the comments, and I'll see you in the next one.